Hello, my name is Colin Cantrell, and I'm here to give a presentation on scaling blockchains. So this has been a topic of great discussion since about 2015 is when the scaling blockchain conferences really began, and it's proven to be a very, very difficult feat to achieve. And many people have been looking at varying types of solutions. So with this presentation, essentially we're planning on making it available for you to understand some of the challenges that we have with the blockchain industry and also some things that we can do to improve that overall scalability. So why don't blockchains scale? Because they rely on technologies that were not engineered specifically for blockchains, such as Google's Level database, which we'll get more into that details on one of the next slides. But essentially, LevelDB was designed as a storage engine that could handle petabytes worth of data, right? Really large data sets, right? And it does this through a type of concept called log structured merge trees, which is essentially appended on top of sorted string tables, where it's just a bunch of tables and you sort them and then you find the right table through a log structured tree, so on and so forth. But one of the issues with it is not necessarily that it's a bad technology, but that it was not engineered specifically for blockchains. There really hasn't been any technology that's engineered specifically for blockchain. If any of you are familiar with the Bitcoin code base, it uses the Berkeley database, 4.8.3 generally version, for your wallet.dat file, right? Which that uses a binary search tree, which is logarithmic complexity. And it also uses Google's LevelDB for the main blockchain store, right? To store some of your indexing files. So, we've started to see a lot of these limitations. Bitcoin upgrading from Berkeley database for the block indexes to Google's LevelDB actually brought significant improvements, because it's not necessarily just about the size of the blockchain or the data, but it's how you sort that data, how you structure that data, which will determine your complexity when you're doing lookups. And blockchains are very read intensive, especially when we're dealing with virtual machines, right? Because some of the states of those virtual machines need to be retrieved from the disk, right? Or sometimes a remote node. So anytime you add these different stages, it increases the overall time, which will decrease your overall throughput and capacity for the single dimensional structure. So as I was saying, the object lookup takes at best O log n, which gets slower as more transactions are stored in the chain. So logarithmic time complexity is ideal when you're dealing with any sort of algorithms. Not ideal would be exponential complexity. So let's say n squared, right? If you have 10 iterations and it's n squared, you end up needing to do 100 iterations, right? For an n squared, for a data set size of 10, where logarithmic, right, could be substantially lower, right? So what ends up happening, you have, I think on average, like 1 million keys in the data store. Log base 2 of that is about 17, right? So each one of these numbers of n, quote unquote, for the disk lookups generally translates into a disk seek. And that is the most expensive operation, where you essentially have to move to the certain position on disk, the physical position on disk. And you have to read that data straight off of that, right? So a seek is your most expensive operation. And so a database storage engine wants to minimize seeks as much as possible, right? And then the operating system will also optimize it through what's called paging and virtual memory, where they will store your files in the spare unused RAM so that you can seek it much quicker and not have to actually hit the disk. Hitting the disk can be very, very slow. So they use also complex cryptographic algorithms that require a lot of computing cycles to process, such as hashing and digital signature algorithms, right? Generally speaking, blockchains use what's called elliptic curve digital signature algorithms. And based off of my personal tests, this is just my computer. Benchmarks are different for different computers, right? But my personal computer, doing a Brainpool 512T1 curve, I multi-threaded was able to get to maybe 7,000 or 8,000 signature verifications per second. So you have a computational bottleneck there, right? Along with these disk bottlenecks. And your data storage engine, right? The database, that is has a big influence over your runtime, because if it takes 17 iterations to find one key, one state, then now you're 17 disk seeks, right, for every operation, where if you can make that one disk seek, it would be much, much more efficient. So blockchains are single dimensional structures. So they essentially are chaining in one direction. So you have a block and it's chained to the next block and the next block. And the concepts of it, I'm sure all of you are familiar, is that if I change a bit, any bit in one of those previous blocks, it's going to break that chain, right? So it's a single dimensional chain that allows you to traverse forward and backwards, right? As one dimension, you could consider that like a line, okay? And so it links blocks together in a finite space, or of a finite space, being able to traverse forward and backward, right? Now, a single dimension can only hold so much information, which is why reality is not one-dimensional. Adding a dimension increases capacity exponentially, and that's very simply mathematically proven. If we have a world with, integer size of 10, and it's a single dimensional world, then you only have 10 possible positions that you can be in. But if it's a two-dimensional world now you have 100, right? 10 times 10, right? Or another good example is 2 pi r, which is your circumference, to pi r squared, right? R squared from r, that goes up to two-dimensional to get you your area, to 4/3 pi r cubed that gets you your actual volume, right? So, every time you add a dimension, you're essentially exponentiating. So, that's why calculus, when you do derivations and integrals, right? The first derivative of a position equation is your velocity, and the second derivative is your acceleration, because you're reducing the dimensions down from your position down to the actual moving position down to the movement within them, right? So you are traversing dimensions essentially, right? And I'm speaking purely in the sense of mathematics, right? And the reality that we exist in is encoded with at least 3 spatial dimensions, and then we have one temporal dimension for time, right? Which essentially designates where everything is within the 3-dimensional space. But because we live in a 3-dimensional space, there's exponentially more capabilities to express and experience, right? Because there's exponentially more possible places for information to be encoded. So blockchains are sequential, right? Meaning transactions can't be processed in parallel. You can do synchronization. Bitcoin Core did a really nice optimization for their synchronization processes, where they downloaded the headers and then they download the transactions and process those in parallel, which that's doable, right? But that's synchronization. When we get to the actual main net processing, when a new block comes in, only one block gets to occupy the same height, right? And if you have competitions over that, only one block wins. And so therefore it's one sequential series of events. So you can really only append and add. If I have a transaction that's dependent on a prior transaction, I have to let the prior transaction be fulfilled before I can process the current transaction. So by nature, the architecture is single dimensional, right? It's sequential. It's one after the next, which is one reason why they have difficulty scaling. So also, common blockchain virtual machines are 256 bits. So what that means is that they operate on 256-bit words. So if I wanted to do a simple computation like 1 + 1 = 2, it could take up to 64 bytes of memory, because each 256-bit integer is 32 bytes, right? So 32 and 32. So what ends up happening is you end up having to do a lot of padding, and you have to do a lot of computation, since physical processors only operate on 64-bit words at a time. That means you have to do 4 times as much computation to do the same amount, right? If I did a simple benchmark test where I took a 256-bit big number, right? Let's just say from OpenSSL or even, MPZ, and I could drop that in, or OpenGMP, I could drop that in, and if I were using a 64-bit integer, and I did 1 + 1 = 2, it would be much faster than if I was using a 256-bit integer, right? So in the real world, 256 bits is not practical. That's pretty much the number of atoms in the known universe, right? 2 to the power of 123, or 123 bits, is more iterations than can be counted to with the known energy of the universe. So that's where the integrity of these cryptographic functions comes from, is that they become so difficult to break, because these numbers are so astronomically large, right? So since we live in more of a 64-bit world, right? 64 bits is around 10 to the 17, if I'm not mistaken. So you end up having about 17 or 18 digits, right, in that number. So, we're talking quadrillions, right? A bit more. Right now, I mean, the world, we kind of deal in trillions, right? Billion is 9 digits, trillion is 12 digits. So, in a global economic system, I mean, trillion's a lot, right? And a quantity of a trillion of anything in the physical real world, that's a lot too. We don't really generally deal with anything larger than billions. Maybe we're starting to get into trillions on just some of the inflationary currencies, but in practical real world terms, we generally deal with millions and billions, right? Well, sometimes touch into the trillions, but in practical real world smart contracts, 64 bits is sufficient. So 256 bits can still be utilized, but not for computation. Okay, and that's one thing that we distinguish with our virtual machine design. So most blockchains use trees for data stores. As I was mentioning earlier, the Google's level database is what's called a log structured merge tree. Now that's just a fancy name for you write it all in memory and then you dump it to disk every once in a while, and they're essentially just big sorted string tables, right? So it can handle a lot of data, right? A lot more than a conventional binary search tree. Like Berkeley database is a binary search tree, and it gets slow. it doesn't handle itself very well. I've tested this directly by running level DB side by side with our lower level database versus Berkeley database, and Berkeley database is the first one to poop all over itself pretty much. It actually will crash my computer if I want to keep going. So when you're dealing with disk seeks and disk access, right, you want to minimize the seeks, and every layer of that tree is one disk seek. So when you're only at 1 million keys, which is not a whole lot dealing with a global transaction network, you're already at 17 disk iterations per lookup, right? So then if a transaction requires 5 lookups, or if it's a complex smart contracting language, maybe 20 lookups, you multiply the complexity exponentially, right? And you're really throttling yourself on the disk. So as the data set grows, the search complexity is logarithmic. Like I was saying, 1 million keys is about 17. And then, you keep going up and it'll go 18, 19, 20, and you'll still be able to get a large data set, but you still are adding these disk seeks ad infinitum, right? You just continue to add more and more disk seeks, right? They're not constant time. So these data store techniques are optimized for read performance, right? But they're not designed specifically for blockchains. And one thing that blockchains do, such as they're cryptographic objects that are always indexed by hash, right? And so your key indexing is the result of the data. So, one optimization we've done with our lower level database is we don't directly store the keys. We store a compressed form of the key through the hash map. And based on my results compared to prior database versions, I have about a 30% reduction in disk utilization. So, plugging the lower level database into Bitcoin, for instance, could save, depending on the size of the blockchain, but you'd save about 30% off of the blockchain size, right? Just by simple optimization of knowing your data structures, right? And designing the disk data storage mechanism to work with that, right? To be optimized with that. So the database and disk access is your fundamental bottleneck for virtual machine processes. If you need to compute on 2 values, or if you're calling another contract, or any sort of complex operations in the virtual machine, it's going to require a disk access. Now, if your disk accesses require 17 iterations, and then it keeps getting slower and slower and slower, what's going to end up happening is your blockchain is not only going to be really big and really difficult to download, but the key storage is going to have a lot of data to sift through to find the basic fundamentals of what it needs to do, right? So ideally, we want order of 1, which means constant time, since blockchains are growing constantly in size, right? And that's how I've always seen as kind of like a holy grail. If we can reach this constant time on the disk access, that's going to be fundamental for blockchains, even when we start introducing sharding techniques. So blockchains rely on Moore's law. Now, this was outlined in the original Bitcoin white paper, and if you see some of Satoshi Nakamoto's original posts, he discussed a lot about the scaling characteristics of blockchain based on Moore's law, where he basically said in 20 years, 30 years, sending a high definition video over the internet's not going to seem like that big of a feat, right? And that's held true for the most part. Especially, the logic is very sound that when you create a block size, you have a linear growth in the blockchain's data set, but Moore's law is growing exponentially, so thus you'll always have spare capacity, right? And that's the premise and the principles behind Moore's law as a scaling solution. But this is not always held true, right? Moore's law is already weakening. It's not exactly what it was said to be. It's not growing as fast as it once did due to issues like quantum tunneling. And if you haven't noticed, processors, their clock speed has become somewhat saturated around 5, 6, 7 gigahertz. You don't really see clock speeds much higher than that. You just see 8 cores, 16 cores, 32 cores, because they're running into issues with the crystal oscillation and quantum tunneling. And when you start shrinking these transistors too close, the quantum tunneling is essentially you have a barrier here, and there's an electron over on this side, and it should bounce off this barrier, but it just sometimes decides to just disappear and reappear on the other side, right? Quantum tunneling. So you have enough quantum tunneling, and imagine this is a barrier for, let's say, the gate, right, or your collector for your or your base, sorry, for your transistor, and you're going to collect electrons on there. What that's going to create is a voltage, and when you induce a high enough voltage, then that is going to switch on, right? And essentially, it's going to be flipping on when it shouldn't be, right? And quantum tunneling also has been destroying some of the processors, right? Like they hop over, and they so we've run into this barrier, right? We're not like at it head on yet, but it's instead of it being this exponential growth, it's kind of starting to form more like a sigmoid curve, right? And I believe as we see more over time, we saw that Moore's law, in the growth here, but as the sigmoid tapers off, it slows down, right? It becomes more logarithmic, and it increases. So modern software, because of this, relies heavily on multi-threading, right? Essentially, multi-threading is having two things happening at the same time, right? That's one thing quantum computers are breaching into, is having actually every bit be able to be a 1 or a 0 or have two states at once, right? So we want to parallelize things because that's going to better utilize the time, which is going to increase our throughput, because when you can do more in the same amount of time, you have higher throughput. So because of this clock speed saturation, software has been optimized in the modern age using multi-threading techniques. It's been adding things also like atomic compare and swap, and that's been designed to help reduce thread contention through multi-threading, right? So there's been all of these really significant engineering feats just to really improve this multi-threading nature of computation, because that's been one of the really significant ways that we've been able to scale computers out, is we've scaled out the cores, right? We've added more and more and more cores. And you have more cores, then that's that many more simultaneous threads that can be operating. If you only have one core, then you rely on the thread scheduler from the operating system to schedule events, but really one core can only really handle one set at one time. So having more cores gives you that parallelization, right? Now, as I was saying earlier, some have adapted synchronization processes for multiple threads, such as Bitcoin Core, as it's been improving their synchronization logic. But still, everything must pass through a sequential bottleneck to append data to the chain, right? Since you have dependence, and the previous block has to be a dependent, and only one block can occupy a height at one time, it doesn't matter how much you're multi-threading, because that block is that block, and it can only be appended at once, right? So the capacity that block has is the capacity the network has, right? It's single dimensional, single threaded. So I know you've probably heard a lot about sharding, right? So let's start to form a little bit of basis on the sharding and see how that kind of ties into all of this. So sharding the ledger is a common response to these architectural limitations, where the idea of sharding is that you can have multiple devices that are operating on a subset of the entire global chain, right? And that gives you this parallelization. It's kind of like having different cores of a processor, but you could think of the processor as all of the computers, and then each device is like a new core, so that you can start to do more parallel processing, right? And that's shown a lot of promise, but it does solve the issue of increasing the issue with the constantly increasing data set size, but it still succumbs to the same issues of logarithmic lookup complexity in the database. So in the end, you're just slowing down the inevitable, right? Yeah, you could have shards, but each shard still going to get slower, right? And slower and slower because the data sets are still going to grow without bounds in each of these shards. So sharding is, I see, a temporary solution to the architectural issues, right? It will only give you higher throughput immediately until it degrades back into the same linear issues, right? So since blockchains are dependent, right? I'm talking like a debit has to be matched with a credit, or a transfer with a claim, or the unspent transaction output needs to get spent by an input, right? They all have dependence. Shards can quickly degrade into sequential bottlenecks, right? And let's say, I'm, spending a UTXO from another shard. I'm going to have to look up that shard in order to process here, which is then going to put my bottleneck on the other shard, and it's kind of merge into this sequential process, right? So getting sharding right is very difficult, and it's also very difficult to get it done securely, right? Because you're splitting up your entire data set, which, that's very good for essentially improving your throughput. But, ultimately you're going to succumb to security issues because now you've got less nodes working on each specific aspect, right? So sharding is very difficult to do. And that's why we haven't really seen, I'd say fully production ready sharded networks that we're talking like some, serious transaction throughput. So why not layer 2 solutions too, right? This is another big thing. Layer 2 solutions like the Lightning Network first emerged in the scaling debates, right? The blockchain scaling debates in 2015, or the scaling Bitcoin conferences, I should say, in 2015 to 2016. But as you can see, this topology over on the right-hand side, I know there's a lot of debate about, that it makes it more decentralized because you're taking away from miners and so on and so forth. But ultimately, the way the mathematics works, okay, is that liquidity is going to be necessary. So if I want to send a transaction to Alice, but I can't open up a channel to her directly because, let's say, Bitcoin charges $1,000 per opening a channel. I only have one channel with the pizza shop we go to. Oh, okay. Well, Alice has the pizza shop too. So yeah, in theory, that's great. We can just transact back and forth with one another. Then we can settle it on the main chain when we're ready. But, what's going to end up happening is these pizza shops are going to get bigger and more people are going to start adding, and then they're going to provide a network effect, right? It's called Metcalfe's law, which states that the value of a telecommunication system is proportional to the square of the participants. So when you add more participants in this little Lightning network, this Lightning liquidity provider, let's call it the pizza shop, it's going to exponentially grow the value of that specific hub, which is going to drive more liquidity into it, which is going to cause more people to connect to it, just like a social network, because they need to send their coins to each other, right? So what's going to happen is it's going to aggregate, right? Because as the fee model, right, goes up, the fees are going to continue to go up. It's going to become more and more expensive. The availability of creating new channels will become less and less and less. So as that goes less and less and less, people are going to be forced to use channels that they already have open with their pizza shops. And it's ultimately going to create these big liquidity pools. And on the right-hand side graphic, you can see them already forming, hub and spokes, right? So it is still, somewhat decentralized, but to me, it creates a lot of opportunities for bad things to happen, right? Liquidity providers can quickly become centralized hubs. They don't solve the root of the issue, which is our fundamental architecture. They're just adding a layer on top of that fundamental serialized blockchain architecture. And the deposit sequence too, it eerily resembles having a bank account, right? I deposit my Bitcoin into this Lightning account. I pay money to open up the account. I keep the account open. I can send my Bitcoins in that little payment network from that little account, bank, and send to everybody else. I can send my Zells. And then once I'm ready, I can withdraw my Bitcoins and settle it back on the main chain, right? Sound familiar? Exactly, right? So one reason I've not really gone towards the layer 2 solutions is I'm not convinced that that's going to maintain the required level of decentralization for these networks to truly take off. We need that level of decentralization by looking at the way the world is. If there's any point that can become corrupted, they will try. They will try. So we need to do our best to make it as resilient against that as possible. And that resilience comes from decentralization. And so everything to me should be on chain, right? If it's not on chain, then it's not as decentralized as it could be. So this presentation is going to outline how we do that. So as I've seen, you guys most likely have probably seen this argument: mining is slow and centralized, right? It creates a centralized arms race. It consumes a great deal of energy, and it tends to create these centralized pools, right? Much like layer 2 solutions do with the liquidity, right? Except, for the Lightning Network, the mining pools are the liquidity providers, right? How much Bitcoin you have and how much liquidity you're able to provide in those channels, right? Now, most of the proof of work is wasted as well. So even though the network's running at a given hash rate, only one hash wins. And that ultimately becomes the block. So because of this, mining pools tend to be the only way people can earn money from mining. So many people have abandoned proof of work altogether to go to pure proof of stake, but that approach in itself has its own issues as well. So where is this all going? We've been designing and implementing new blockchain architectures for over 7 years. The project is called Nexus. I'm sure you presented on our security-focused operating system design last year. And essentially, we have taken the concepts of pretty much that have been outlined to us just through simple mathematics and reality to basically achieve maximum throughput in a multidimensional sense, right? So what we've done now currently is we're still in the single dimensional phase, which is called Tritium. It's Tritium and Tritium++. We're on to Tritium++ right now. Tritium was released a couple years ago. And some of the benchmark tests that I was able to do, this is a live network over localhost, okay? So it didn't have bandwidth as a limitation because I wanted to see just the pure processing capacity. So this was all on one computer, and I had about 8 different command prompts, scripts running, just hammering the node with transaction requests. And then I had a node processing the transactions. So I'm sharing the same resources that's producing the transactions and processing the transactions. And that tapped out at about 10,000 to 12,000 contracts per second, which is about 5 megabytes per second. And most of my computing cycles were going to the generating of the transactions. It processed straight through the chain, not a problem. And so one of the reasons that we're still in the single dimensional phase is, as we multiply out exponentially by adding dimensions, right? Think x versus x squared. We also multiply our margin of error. So we're focused on perfecting the single dimensional blockchain first to get all of the bottlenecks out of a single dimensional layer, because that single dimensional layer is then going to be created into a multidimensional object. So if we have inefficiencies in our fundamental layer in a single dimensional sense, that's going to multiply out, right? So we wanted to clear and get as many bottlenecks out as possible. And each shard is not going to process 12,000 contracts per second. That's showing just a maximum on my specific hardware with bandwidth not of an issue to see how well everything processed and benchmarked. And I was certainly very impressed to be able to reach that level. Our register-based virtual machine operates anywhere from 10 million to 70 million instructions per second, or around 10 to 7 megahertz. So this virtual machine, it's a register-based architecture. I went down into the really significant details. I actually created a register-based virtual machine that ends up being a register memory manager with 64-bit registers that fit directly in the frontside cache of your processor, right? Since it's not amortized, it's one for one. It fits in. It's software designed to be as close to the processor as possible. So it can really run everything just right off the processor, so you don't get these memory latencies. And so that's how we were able to reach 10 to 7 megahertz. When I actually wrote that, going from a different data object, it substantially improved the performance. So our database also is order of one. And I've tested it up to 500 million keys, and it operates at 450,000 reads per second compared to Google's LevelDB, which, as I said earlier, operates Bitcoin and Ethereum. And that tops out at about 80,000. And that's being very generous. That's tops out. On average, it does probably about 40,000 reads per second, 50,000. But if I flush the pages, right, and I start over fresh, or I try to write 1,000 keys and then write 10 million keys and then read those first 1,000 keys, the read performance goes down to about 10,000, maybe, if that 8,000. But the lower level database stays 450. Sometimes it can go 150 to 450, depending on the paging conditions, right? But it stays constant time. And I mean constant time as in a consistent number of operations. So it only requires 3 disk seeks to read any record of any size, anywhere, right? And I've done that through a combination of, I guess you could say multi-dimensional hash maps and multi-layered Bloom filters and Fibonacci linear probing for forward and reverse linear probing and a couple other aspects. But that database has been pretty much, I've been developing it since about 2016. I got a really, the last iteration was developed and deployed with Tritium, and this next iteration is going to be deployed with Tritium++. And as I said, it's constant time, straight through. So on average, my node will process anywhere from 30,000 to 100,000 contracts per second. And what I mean by process is, as soon as you receive the block, and you process all the transactions, and then commit that to disk, okay, that time, right, of processing all of those, that's processing the virtual machine, all of the bytecode, all of the transactions, that time is, about 30 to 100,000 contracts per second. It's really, really fast because of the way that we design it with the pre-states, and we package the pre-state in, so a contract object is like a self-contained object. And you can take that contract object and it has everything it needs to self-execute. Because with us, a contract is a register script, right? It contains a register pre-state and post-state and a set of operations. Okay, there's a primitive operation, which is like debit, credit, read, write, move, transfer, claim, condition, validate, like those are basic primitives. And then we have the conditional virtual machine that is essentially a conditional contract that's appended. So you have a primitive operation that is controlled by this conditional contract that then contains a register script that it's operating on. So a contract by nature operates on one register at a time, okay? And there can be 100 contracts in a transaction for Nexus. So this ends up being very, very fast. And it also solves the issues with reorganization of the chain, where we can revert back to prior states without having to reverse the computation. We can do it reliably, which means if I have to disconnect a block and reconnect a new one, instead of having to just append with uncles, right? Because as far as I'm aware, Ethereum has a difficult time changing the state tree. We're able to actually just revert right back one, right? And we also, like I said, the contract is self-contained. So this becomes really important when we get to the multidimensional sense, because right now a contract is just bound to a transaction object. And the transaction object is bound to a block, right? So the transaction has its own Merkle root with all of its contracts, so that the contract and its hash can actually be used as a Merkle proof. So you really only need to have your block header and your transaction header, and you can just plug any contract in there, right? And the contract is self-contained. So I don't need to know everything that happened before that contract happened. As long as I have that contract and I have a valid proof into, a Merkle proof into the block, then I know that that pre-state is valid, which means this could be the 100 millionth transaction operating on that specific register. All I need is that 100 millionth transaction, and boom, I have it, right? And then we'll get into this in a little more detail, but the signature chain architecture allows us also to not need all the signatures, right? It's a chain of signatures, so you can actually just keep, your head and your tail. And because it's a chain, right? A signature chain is kind of like a mini blockchain. We can actually discard aspects that aren't needed anymore, right? Because we have these proofs. And when you have a proof of a chain that's sealed on both ends, then you don't need certain pieces of information between those 2 points, right? So that allows a very significant type of pruning of our signatures and our public keys in the signature chain, which is a massive reduction in the blockchain size requirements. And we do this securely, right? It's just as secure as keeping the signatures. That's what's so beautiful about it, right? And that's how you know you have a good architecture, when everything fits together really beautifully. And you start to find all these other adverse effects that you didn't intend that ended up being really valuable. Not to say that about signature chains, but the pre-states has definitely been really fun to get into. So our architecture is multidimensional, right? This is where we start getting multidimensional. So a single dimensional chain locks a sequential series of events behind the head of the chain, okay? We've expanded this concept into creating a 3D lattice-based chaining structure. So as you can see in the below diagram, there's that center root cube. Think of that as the very center. Think of the 3-dimensional block as like a Rubik's cube, okay? You got your 3 and your 3, and you got that very center cube, okay? And based on perspective, that center cube can project into the other corner, right? The topmost corner and the backmost corner in the center. So that creates this chaining through the layers in this way. So think of the base layer as like a lattice. It's like a crystalline lattice. So you have, these are your shards and your state channels, and then you add a chaining on top. So you chain them to the side. So what ultimately happens is this root hash right here, okay? This root hash ends up being the final reduced copy of all of the hashes. So I need to know from here to here, right? And what that tells me is that this entire structure now is a 2-dimensional chained structure. So that means if I change any bit anywhere, I'm going to break the chains this way, and I'm going to break the chains this way, and ultimately I'm going to break my final root. Okay, so instead of thinking in chaining little blocks together, we're chaining objects, right? And we're layering these objects together. And each one of these layers, okay, the L1 and the L2 and the L3 layers, they form different consensus mechanisms that check and balance one another. And each layer is responsible for a single dimension of chaining, right? So they're only really dealing with one dimension themselves, but then those get stacked together and reassembled, right? Kind of like, you know, a factory working on a simple piece, and then all of those are reassembled into a larger object, okay? So this root cube is a very important part because this kind of contains the reduced of all of these, so that your root cube and its final hash represents the hash of the entire 3-dimensional object, okay? And that means that if I change any bit in any one of those directions or places, it's going to break that root hash, okay? It's going to break the lattice. So if I wanted to attack this, okay, and I wanted to attack it from the L1 layer, I would have to build a new lattice. If I wanted to change or insert anything in this history, I'd have to change 2 dimensions of history, because I'm not going to be able to reassemble these chains, right, that happened afterwards. So you create this very rigid 2-dimensional object that has a lot more capacity, right? So you have this aggregation, just like reality. We live in multiple dimensions so that we can store more information. So we're chaining in multiple dimensions so that we afford ourselves this additional capacity. So think in shapes, not lines, okay? An artist evolves from stick figures to beautiful works of art, capturing the full multidimensional picture in their skill, right? So that analogy is basically saying, you know, when we're kids, we make stick figures, right? That's single dimensional, right? Lines, right? Then as we get older, we start learning about shading and circles and spheres and cubes, and we start expanding out. I know it's a projection, but what we're doing is we're mimicking those different aspects of those dimensions. The shades come from your depth and your light, right? So a blockchain is an informational recording system, now providing an indisputable ordering and associations of different pieces of data. So creating a multidimensional chaining system provides us the opportunity to store more data in parallel by using the natural formation of a shape to delineate shards. So as I was explaining, each one of these is our shards, okay? Let's just see a simple 4-shard object. Now, those have a chaining structure across, okay, so that they end up creating a final multidimensional piece. Now, this shape is what would be swapped in or out. So if I wanted to attack, I'm going to have to create that entire shape, a fork of that shape, right? And I'm going to have to also have that shape accepted by an L2, the L2 layer, right? Which, if there's anything that's in conflict with another one, it's going to be looking at the total reputation. So the depth or the significance or the weight of this data is fundamentally comes down to your trust and your amount of resources that you've contributed to it. So these L1 layers ultimately are going to aggregate their trust together, and they're going to join together to create this shape that then has an overall higher exponential weight than a single participant would be able to pull off. So this allows us to basically, with a higher degree of security, do this parallel processing, because we have this checking and balancing happening in between. And the reputation essentially prevents somebody from being able to just buy their way in or try to put up a bunch of nodes, right? The reputation system is somewhat like an immune system, where it knows itself because it knows the participants that it's been working with. All of the people know who they've been working with. And so if a new person comes in, they have that opportunity to join the consensus process, but other people will be able to identify malicious behavior because they'll know what a trustworthy node does. And so when a node comes in and starts trying to spam, or maybe they try to split a shard and create, a conflict where they have a conflicted transaction, with Nexus, you can identify a conflict very easily. And we do that already in our memory pool in a single dimensional way. If you produce another transaction that's in conflict with one, that transaction is not going to relay. And other nodes will actually flag a block produced with that transaction as conflicted. And that block won't relay unless somebody builds a block on top of that, right? So, there's a lot of really simple and elegant ways that we can identify this malicious behavior. And that's going to be done on the per shard level, because each one of these shards is agreeing with their neighbor when they send, their reduced, hash across as they're building the lattices, right? And think of each one of these as having a different interval. Generally, a three-dimensional block will be at about a 1 minute interval. So the production of the L1 and L2 layers will be done over the course of the minute in real time, right? They're going to be added independent in real time. And then the miners are in the L3 layer are going to follow and then seal up the minute behind, right? So multiple consensus layers also are responsible for their own dimensional chaining, as I was saying, checking and balancing each other. So, we deal the L1 layer, moving shards, chaining in this direction, okay, and then passing the hashes over. And then we have the L2 layer that's helping create the cross-link hashes, okay? And that's combining together these, so they're adding that on top. And then the L2 is also going to receive these hashes from the mining shares on top, and it's going to weave that into the root cube, okay? So I'll get more into the details of the L1 and L2. So we ultimately get increased security and decentralization. So as I was saying, imagine it like a Rubik's Cube. This picture on the right kind of somewhat does it justice, right? Where it shows you that center cube, that's an important aspect, because that shows us the chaining diagonally, right, through each of the vertexes, vertex to vertex, right? And that forms, those chains form that vertexes of that center cube. That center cube then finally hashed gives us the root hash of the block, right? So by having these multiple chains in all these different directions, we have these different lattices and these checking and balancing. So, as I was saying, instead of swapping out a whole block, we're swapping out pieces or lattices and shapes of these objects, right? And we're resolving conflicts between the two. So what that ends up doing is an attacker now has to attack 2 dimensions instead of 1, right? And then even another dimension on top of that. So it exponentially increases the resources required to attack the chain. Then when you add reputation into the system, it becomes even more difficult, because you essentially can't buy your way in, right? And so all of the people that have existed prior have a protection, right? And they can identify these malicious actors. So these lattices are woven together in up to 3 layers. And as I said, it requires an attacker to coordinate many more pieces to create a competing lattice structure that also has to have exceeding trust, right? It has to be beyond the amount of trust and the weight, which just becomes exceedingly more and more and more difficult. Even with somebody with a lot of mining power, they'd only have really influence over one dimension of the structure, right? So that's why we believe combining together these multiple layers of consensus are really important for the long-term decentralization and security of the systems. We can't rely on just one alone, right? Just like there's 3 branches of government to check and balance each other. These 3 consensus layers check and balance one another. So it requires an attacker to compromise all 3 of them to try to compromise the 3-dimensional block, right? And then to exceed the resources that everyone else contained. So we use these 3 layers of consensus. Our 3 layers are the L1, the L2, and the L3. The L1 layer is responsible for creating single dimensional chains on the Z-axis, as I was saying earlier. And there can be multiple L1 shards or chains, and think of them as their own little blockchain. Okay, so since it's a single dimensional object, they're their own individual blockchains. And those can process in parallel, okay? And then those, as I was saying, are linked across the x-axis and then the y-axis. So the L2 layer is responsible for weaving shards together along the x, right? And it's also for resolving conflicts between L1 shards. So we don't want shards to have to resolve conflicts between each other. For one, they don't know they have conflicts with one another if they do, because they're in their own shard. So the L2 layer, in an aggregated processing environment, it's able to take these L1 shards, and then it basically has a consensus process to deciding if there's 2 conflicting forks of an L1 shard, that they will ultimately help make that decision of what one of those is included based off of the highest amount of trust and weight. And then other nodes will obviously have to agree from the L2 layer so that you create this really robust consensus mechanism. Now the L2 layer is weighted by stake, okay? And it's also got trust involved in that as well. So you have to build up trust over time by consistently contributing resources to the network. But we also have to have a stake, right? You have to have some Nexus there available to lock it up to be using it for this consensus process, okay? So the L2 layer is responsible for the computation of the final root cube, right? And it becomes the final 3D block hash. So the L3 layer, okay, is the top layer, and it's responsible for the seal of the L1 and L2 layers. So as I said, the L1 and L2 are built in real time, okay? And then once those finish their minute interval, then the miners are going to submit their hashes for the prior interval, right, to seal up the prior block, and the L2 nodes are going to receive that and then create their final seal of approval, right? And then the miners are going to start hashing on the next set. So the miners are 1 minute behind, okay, and everything is going in real time, so that they're kind of wrapping up and sealing up the blocks, right? And the miners have their own chaining structures as well. So the L3 layer it's driven by shares. So it's not one hash rules all, okay? It's a consistent process. So you as a miner will be searching, right, off of a certain set of data inputs and a certain nonce values, and you'll be searching is to find the hash that has the highest amount of weight, okay? Because you'll want to have your highest amount of weight because that's going to determine how much you get paid. So you're going to have incentive as a miner to search for one hash that brings you the highest weight. And we're going to make the weight slightly exponential, probably like 1.618, or n to the 1.618, something in that range, so that you'll get exponentially more resources for higher weighted hashes, so that you won't just try to spit out 10,000 hashes, because you'll make less money with that. And there will be a certain threshold, a difficulty threshold and stuff, right? But the idea of the L3 layer is to utilize all of the computing power possible on the network by having everybody be able to contribute that hash. And all of those hashes are based off of the same data inputs that agree on the same root cube, okay? So by hashing and submitting a share as a miner, they're verifying that they have checked that root cube and that it is a valid cube. So every one of these miners adds an additional layer of security onto it, where with it works with Bitcoin is one hash wins and that's it, Okay, and that person could be lying, they could be trying to double spend, and it doesn't matter because the highest weighted hash wins above anything else. This allows that to be split up and create a secondary consensus among miners, right? That really ultimately decentralizes the mining protocol much more. And this will more correctly and adequately utilize that computing power to allow people to fully, receive that security from it. And I believe mining is very important. It creates a lot of security. So correctly utilized, I think it can be a very powerful instrument and proof mechanism, which is what we've done here. So don't throw the baby out with the bathwater, right? Mining by itself has its own issues, but when combined in a hybrid consensus mechanism with other mechanisms of proof, it becomes highly effective and very secure, right? Proof of stake by itself, again, can be dangerous when market cap is small, as it becomes trivial to buy a controlling interest in the network. And when we're talking about creating these systems that have the potential to, stand up against, the big banks, they have trillions of dollars at their disposal. So, it's very easy to buy, into those voting systems. So we think, we want to combine these multiple consensus algorithms and do it in this multidimensional structure, right? And we get the best of all. And that goes to provide additional security to the shard and the state. So how do we shard the database? Data sharding becomes very problematic, especially when you have a dependent in another shard, right? Like I have to credit a debit from another shard because you're quickly going to integrate into sequential, because in order to verify that credit, I have to verify the prior debit, right? So how do we operate this without needing to synchronize this global state for processing? What we're doing, and it's a really fun way to use Lisp, but locator identifier separation protocol essentially allows you to create a single mapping, a single address on the internet that allows you to change Wi-Fi or go to a different place, and you'll still have the same address, right? So it's like having a phone number that doesn't change on the internet. But what we're doing, since Lisp allows us to create these addresses for any IPv6 crypto EID, an authenticated EID, is we're actually going to take a reduced checksum form of the data key, and we're going to use that as our index to look up. So we can actually store a node that has that piece of data, just registers with the mapping system and says, hey, I'm servicing this IPv6 address. That IPv6 address could be 128-bit hash of the reduced key and index of the object that you're looking up. And what ends up happening is you really can just open up a TCP/IP connection to that hash, to that IPv6 address. And then the other node that's servicing that obviously would have to have their own server running to receive and deliver that data back. But we create this globally synchronized database where we don't have to iterate, distributed hash tables or, do all these complex lookups to try to find the object in a sharded state. Is that when one person writes into that state, right? When I write to that IPv6 address and I write that in and I write it with a proof from the chain structure, okay, other nodes then I'll write that simultaneously. So instead of it being I write it and then I send it off to my nodes and then they write it and they send it off to their nodes, which is generally how the propagation works in peer-to-peer networks, everybody writes that in at the same time. So you get this parallelization, but you also have this globally accessible common interface, okay, for data objects, so that you don't need to seek and find and what shard is this one on, or what mapping lookup, or what IP addresses, or what cluster, or what. You just open up a TCP connection. You open up a socket connection to the data object, and the nodes that are servicing that give you the object, right? So that gives us a really common interface and a really beautiful way to handle it too, where you start seeing the internet slightly differently, with these addresses being identifiable. And when we get to the Nexus protocol, we'll afford larger EIDs, right? Because we're developing the one stack, which Open Nexus execution stack, that allows you to decouple this identifier from your locator, right? And our identifiers will most likely allow 256 bits just for cryptographic operations, cryptographic objects, anything like that, right? And since each hash is generally supposed to be unique, okay, based on the input, data input, no two data inputs should give you the same hash. you won't really run into collisions, right? Hashing your objects and having the hash of your object be the lookup address, because it becomes very nice because you do lookup, you grab the object, and then you rehash it and you make sure that it matches the address so you can tell if it was tampered with. And then as long as you know that hash has a Merkle proof into a root cube, into a 3DC, right, into a three-dimensional block, you know that that was a valid object. And so just as I said, the contract is self-contained, I can download a contract from somebody or download a contract from my SIG, or even just download my SIG chain, and only takes a few hundred megabytes, and you got the Merkle proofs all the way there, right? So it fits together really nicely, right? And the idea of a three-dimensional block is that you won't need to synchronize anymore. We shouldn't need to synchronize anymore if we do it correctly, right? The reason we have to synchronize is because everything's locally bound, the computing. But as we start adding out these different sharded parallels, then we open up a lot of really unique new opportunities. So use what's been proven to work, okay? Most virtual machines are stack-based, like the Java virtual machine or the Ethereum virtual machine. Modern processors have what are called registers, okay? And these store values being operated on, which are more efficient architectures, okay? So we don't use stacks in computers. They're just the old tape, those are slow, okay? We use registers, and register lookups are order of one, they're constant time, right? And we're able to reach very, very high throughputs. So with our register-based virtual machine, as you can see above, that is a live demonstration showing a payload of 20 megabytes. This particular instance was doing a block every 5 seconds. So that payload right there was about 4 megabytes per second and 12,000 transactions per second, or 12,000 contracts per second. So we doing that with, a lot of aggregation. And like I said, this is a single dimensional chain. This is showing, your theoretical maximum processing per shard. And like I said, we've wanted to protect, or we've wanted to perfect a single dimensional chain so that as we start adding more and more shards, we don't multiply our inefficiencies, right? We don't want to do that. We don't want to multiply our margins of errors. We want it to be as clean, mean, as fast as possible, because the faster it is, means there's less instructions that the computer needs to operate it. When there's less instructions, that means it takes less battery life, it runs on more devices, and it scales more, right? So we get as close to that bare metal as we possibly can. And we've done that with the database and our virtual machine, which I said operates, up to 7 megahertz at certain circumstances, just because we built it using registers and built our own memory manager and all that, right? And we don't rely on external dependencies that were not created for blockchain. Our database, the lower level database, was designed specifically for blockchain, right? So we're adding more dimensions. We consider a blockchain as a subset of our architecture, right? The blockchain is like a single shard. A user level identity called a signature chain gives us this signature aggregation and other benefits. As I was saying, we only need to keep the head and the tail. We can discard a lot of the stuff in between. We can discard pre-states. All we need is the most recent pre-state that modified that register, and we can discard all of the other prior pre-states. So even, the raw skeleton of a single dimensional structure is extremely efficient because we can prune out so much, and it's also self-contained. And, with that contract being self-contained, you can just broadcast that contract to anybody as long as they just have a set of, headers and, some other basic Merkle proofs. You have everything you need. So the L1 state shards resemble this single dimensional blockchain, and they're linked across the x-axis. In order to change anything within this lattice, it would require redoing all the work that created it, causing exponentially more resources required to attack each given lock level. So as we add more dimensions, we add exponentially more capacity. And with that exponential increase in capacity and exponential increase in consensus, then we now have an exponential increase in attack resources to attack it, right? Because that many more people can fit within the consensus system. With Bitcoin, very few people can contribute to the mining, right? Or, own a mining pool, right? It's all very well oligarch. It's a bit of an oligarchy, right? And that's just because normal people can't gain access to it. So the point of the L1 layer is to give more of those people those capabilities to start getting in and a part of the consensus. And then that starts forming the foundations for a decentralized autonomous organization and the different voting groups that will regulate the entire system or govern Nexus. So in conclusion, we're currently deploying Tritium++, as I was saying, the last update using a single dimensional architecture. So we've got the goal for Tritium and then Obsidian, and Obsidian to reach the highest capacity we can in 1 dimension before expanding to 2 and then 3. Amine is going to be adding these shards and these sharded layers, these sharded lock layers, but it's going to be adding the shards as a proof into the block, right? So you'll still be able to process over a regular classical blockchain. You'll have to opt in to a shard on Amine. So, the main Nexus blockchain right now will, you basically have a bunch of proofs in the block, and that proof can be a legacy transaction, a Tritium transaction, or a checkpoint for a hybrid network. And then, we add one, which is going to be an Amine shard. And then essentially that allows people to volunteer to enter into the sharding system. It gives us a nice runway in the deployment to also make sure that there's no screws loose, everything works as it should. And making sure that we see that throughput. And then the final Obsidian is going to be that wrapping together where we're going to take that linear blockchain. Amine's still going to have a linear single dimensional blockchain, but that's going to be on top of these shards, right? And those shards are going to kind of still be inputting, into that, but the block is still going to be found with 1 hash rules on and Amine. But we still have 3 consensus mechanisms already, right? The proof of stake, and the hashing, and the prime. But then when we get to Obsidian, that's the final bow wrapping up the whole 3-dimensional block. And that's when it'll be a full 3-dimensional block, right? And so this has been a very interesting journey developing this technology. And it's been very fun. I used to dream about, a 3-dimensional block. What would that look like, right? And it's been really cool to see it all materialize and to see the results as they have been. And so I appreciate everybody taking the time for this presentation. My name is Colin Cantrell again, and I am the principal architect and lead engineer of Nexus and the Nexus protocol. You can find out more information about that at nexus.io. And if you'd like to get involved, we're a community-driven project. It's not a corporate, type ICO. We've never done an ICO. It was, mined from zero. The blockchain was launched in 2014. And so we've been around the block quite a few times. And that's one reason why we've been able to develop this technology and why I've spent so much time perfecting the architecture before we actually gotten to fully implementing it or even sharing too many details about it. So this is the first time I've actually done a really deep dive on multidimensional chaining. So I hope everybody really enjoyed this. And I certainly enjoyed the presentation. And thank you very much.